Okay, good morning. Sorry for the delay. It was supposed to be a tutorial by Omri, but he was called for the army, so you'll have me instead. And we're going to talk about self-supervised learning. You started discussing that topic last time with Tali, and she talked to you through the principles and the classic ways of self-supervised learning. Today, we'll go over a few methods that are more recent and more popular that were based on the principles that Tali showed you last time. So just a reminder, in self-supervised learning, So in supervised learning, we have labeled data, which is usually hard to come by because labeling is a very tedious task and requires some expert knowledge. And we train the supervised model based on the labeled data. And we got both features and classifier or a head for a specific task that the data was labeled for. And the knowledge for the features and for the completing the task was actually came from the labels in the data. This is where the knowledge for the model came from. However, in self-supervised learning, we have unlabeled data, and usually we have much more of this because it's usually easier to come by the raw data without any labels. Then we have some self-supervised training, some pretext tasks. These are the kind of colorization or completion that Tali talked about last time. And from this self-supervised training, from this pre-trained task, we get features that are usually, if the task was good, they are meaningful and helpful. We can then supervise and fine-tune the resulting features. So we can benefit from the pre-training from the features by fine-tuning with much less labeled data. And we have representation learning, actually learning some structure in the data. So today we're going to talk about three methods for self-supervised learning. The first is self-distillation with no labels, which is called DINO for short. We'll talk about mask auto-encoders and about contrastive language image pretraining. And these are kind of the main directions that exist today in self-supervised training. So we're not going to cover all the material, but we're going to give you a taste of these directions that exist. So let's talk about DINO. So DINO is a distillation with no labels. And before we talk about DINO, about self-supervision, let's talk about what is a distillation in the first place. What do we mean by we distilling knowledge from a model? So you can do distillation in the context of supervised learning. So suppose you have labeled data, you train a model, and you train a very large model because you have time, you have resources, you want to get very good performance. So you train a very large model, and it performs very well. But now you want to be able to perform this task with much fewer resources. You want to, for instance, to have it run on device, on edge devices, and this model is too big. So instead of training from scratch on the supervised data, you want to use the knowledge the model learned. So given an image, a classification model doesn't output only the label, it outputs a probability vector over all the labels. So it doesn't just say this is a cat in the image, but it's a cat. It slightly looks like a dog and definitely doesn't look like a bus. So this additional information is actually very valuable. So instead of training with binary labels, these are the discrete labels that we have in a training set, we can actually train a model using these rich probability vectors that the teacher has. So now we can have a small compact student model and train it on the data, but instead of using the discrete labels that we have on the data, we are going to use the probability vectors that the teacher has. So the inputs are going to be the images from the data, but instead of discrete labels, we're going to use these soft labels from the teacher. This actually proves to be very efficient in training the student. So if we train the student only on the labeled data, like we did the teacher, usually it will perform slightly less than if we do this kind of distillation, taking a very large model and use the rich information it provides to the student.
In effect of all the probabilities of all the labels?
Yes. And you have some additional knowledge there that you don't have in the discrete labels that you have in the data.
And the output is the same vector?
Yes. So the output in a classification model is the vector of probability over the classes. So now, instead of training it with binary labels, you have these soft labels that actually says, okay, this is a cat, but if you are making a mistake towards dogs, it's not that bad. But if you are classifying it as a bus, then it's a very bad mistake. Yes.
Have they tried, instead of looking at the probability for like one level before that, seeing if they match this level?
So you can do distillation with intermediate features. We are not going to get into this, but yes, you can think about of all kinds of distillation. This is a very broad topic, and we are just scratching the surface here. So this is distillation with a trained model. So we have labeled data here to train the teacher, but in DINO we don't have labels at all. This is a self-supervised approach. So we're only going to get images, and we are going to train both the teacher and the student at the same time. So we're going to have a student model, which is an encoder, which is the backbone that we want to train. That is the feature extraction. This is the representation. It can be a transformer, it can be a ResNet, or whatever we choose. And we have a teacher model. Again, both are untrained at the beginning. And we're going to take an image and take crops from that specific image. So we're going to take very large crops and give them to the teacher. So the teacher sees kind of the bigger picture here. And then we're going to take smaller crops and feed them to the student. We're going to apply some augmentations on the crops, like color jittering, flipping, and things like that, some local augmentations. And then we're going to look at the prediction of the teacher. So the teacher is going to classify the image into some arbitrary labels. And the student is going to be trained to match the labels of the teacher. And we compute the loss between the prediction of the student and the teacher, like in a distillation. And we're going to propagate gradient only for the student. So the student is going to be updated in order to be able to predict the teacher's output on these labels. And we are going to update the weights of the teacher by taking exponential moving average over the weights of the student. Okay? So basically, the student only looks at small crops of the image, and it needs to predict some label that the teacher assigned to this image. But the teacher sees the bigger picture. So basically, it needs to fit object parts to objects. Yes?
What is the centering doing the teacher model?
Okay, we'll touch upon that in a second. But we don't have labels here that are predefined. So the labels that the both teacher and student are predicting, it's some arbitrary dimension. We can decide on 5,000 labels, 1,000 labels, or whatever, but they need to agree on these labels. So we don't really know what the labels that they are teaching, but they need to agree. So if they need to agree, they have two options to shortcut this. They can either predict like uniform probability over all the labels. Then they will always agree, regardless of the image. The loss of this training will be very low, but it's meaningless. So in order to prevent that, we add temperature to the softmax. So softmax takes the logits and turns them into probabilities. We can adjust the temperature so it would be spiky. So it will be far away from uniform. Another shortcut they can do is to agree on a certain label and predict all the images for that specific label. So for instance, they can decide on label 500, 500, and they will always predict label 500, regardless of the image. Again, they will agree, the loss will be very low, but they don't learn anything. This is what the centering is doing. It actually removes the mean, like the bias of the labeling of the teacher. So if the teacher always predicts the same label, the centering will remove this label and will make it very difficult for the teacher to predict the same label over and over again. It has to be different every time. So by using temperature and centering, DINO avoids collapsing into these trivial shortcuts. Okay? Yeah.
The teacher is trained for the student?
No, they are trained simultaneously. So the student is updated with the gradients, and the teacher is updated by a mean exponential mean over the weights of the student. So they are copies of the same model. They are initiated in the same way, but the teacher is seeing average of the weights of the student.
Average.
Yes.
And we don't have any labels? Like,
No, there are no labels here, only images.
so how can they know this is the
They don't know. The labels here are not semantic labels. They are arbitrary labels, but they need to agree. And yeah,
What is the cost function?
it's the cross entropy loss between the probability of the teacher and probability of the student. So they output probability over some set of labels, which is a hyperparameter of the training. So you can start, say, 5,000. They recommend, I think, even tens of thousands of labels. And they need to agree.
And this is backwards on the down part and on the upper part.
So the gradient is only propagated to the student.
Only propagate.
Yes, the teacher is updated by taking the average, exponential moving average of the weights of the student. So we make an update to the student, and we take these new weights and average them with what the teacher has. So basically what we have here, we have the teacher can be quite arbitrary, but it sees the bigger picture. And what the student needs to know is that it gets small crops. It needs to see what is the bigger picture this crop came from. This is how it needs to match. So actually, where is the knowledge in this system? So the knowledge comes first from this concept of parts and whole, that the student needs to figure out what is the bigger picture when you only see small crops. And there are also these augmentations that actually have a lot of prior knowledge. What do we care about and what we don't care about in the appearance of images? Okay? So it's the bigger picture that the teacher sees, it's the small crops that the student sees, the augmentations that actually tells the system what is important and what is not. So if we flip images, then you don't care about left-right symmetries. If you change the colors, then you are more sensitive to the content rather than the appearance of things, and so on and so forth. We have this centering and the temperature on the softmax to prevent this system from collapsing to trivial solutions. And the exponential moving average is used to stabilize the system so that the teacher has some stable way of prediction, and the student needs to match these kind of predictions on all images that it sees. Yes, just
In terms of parameters, the size of the student and the teacher are identical.
they are identical. They have to be identical, otherwise you can't do the mean.
So
Over the-
the only advantage is that the student actually gets smaller pictures. This is what makes it lighter.
It's not lighter. So in distillation, we had big teacher and a light student, which made sense. But here we are distilling the knowledge in a self-supervised manner. So we train the teacher and the student simultaneously, not one after the other. Yes.
So, I mean, the student model and the teacher model are identical, basically.
Yes.
Yeah, if we're taking the teacher model using the average, why don't we have another just distribution, shortcut distributions, except the uniform one and the one label? I mean, maybe we can learn some just another distribution apart from them that is useful, that is useless, yeah, and it's some kind of shortcut for.
So what kind of distribution that might be? So you have different images and different crops that the teacher and the student see. So even if they are identical at the very first iteration, they are identical, but they are seeing different crops, different augmentations of the same image, and they need to predict that this is the same. So they need to predict different labels, otherwise the centering will prevent the constant label solution. And they need this label to be unique because the temperature makes the softmax spike for a specific label. So you need to predict different label for different images, but for the same crops, they need to match. So in a batch, you actually take a few images from the data set, and for each image, you have these different crops for the student and the teacher, and they need to agree on the same crops for all images. So I don't think they have much options for shortcuts.
Do we add temperature only in softmax of the teacher?
They have same temperature for both the teacher and the student, but it's different. I don't remember who has the higher temperature right now, but yes.
How are the models the same size if the input is different sizes?
It's not a problem. So for instance, if it's a convolutional network, then it's it's not a problem. Actually, for transformer, it's even an advantage in a sense that you need less tokens for the student. Okay, so we talked about the augmentation, the global local cropping, and the sharpening and the centering that prevents so
One more question.
yes.
If the network are the same, so how you feed the different inputs, different size of input, or there is it operating? I mean,
No. So as I've answered before, if it's a convolution neural network, it's not a problem. So a convolution neural network can work on arbitrary sized inputs, and you do the pooling at the end. If it's a transformer, then it's just the length of the sequence of the token. So you have different length of sequences of tokens. So it's not a problem. And you don't need to do any padding. So during inference, we take an image. We don't need to crop it anymore. We just feed it to the trained student. And then we have representation, features, and we can now use these features to do supervised training or whatever on top of the trained features. And then we can actually give meanings to the images based on a very small labeled data set.
Is it because of the different sizes of images and the parts of the whole that we're sure that the labels that they will come up with will correspond to useful labels?
I don't think anyone checked what are these labels that they learned, what they correspond to. I don't think it is meaningful.
No,
eventually,
a label for zero and not a label for grassy.
So to get these labels, you need to train this supervised head. So you had a head for the DINO loss that labeled the images into this arbitrary space. You throw it away. It's useless, but you use all the backbone that you trained, all the representation, and on top of the features, you learn in a supervised manner how to classify. And this time, because you have the supervision, you know what the labels are. You assign meaning to them.
How much smaller does the training set has to be? I mean, how much do we actually gain from these?
So I think they showed experiments on ImageNet, and the training at this stage was done with fractions of ImageNet, or they showed that they did self-supervised on a huge data set and then only fine-tune on ImageNet and get better performance. But it really depends on the task. And we also showed, not only us, but many people showed that you can actually work with these features with very few labels and even in a zero-shot manner.
But taking the crops that are meaningful, it's also a hard task. Isn't it easier to just give it
the crops are arbitrary. They are random crops.
They are random crops?
Random crops, yes. We don't know anything about the images. There's no supervision here. But the fact that the teacher sees large crops that actually captures most of the image and the student only see very small portions, it gives a lot of, it's a very challenging task, and actually what makes DINO actually learn good features. Another thing we can do is we can, if we train a transformer, we can actually look at the attention head of the trained transformer, and we can actually look at the attention maps for different heads at the last layer of the trained model. And we can see that it attends to different regions in the object or the foreground. And we can also look. No. So this is the right-hand side is the attention maps from a self-supervised DINO, and the middle one is from a supervised. And you see that DINO learns much cleaner attention maps. There are no speckles in the background. So even the attention, that there are no supervision here, is much more informative than what the supervised model learns. Also, if you try it on images outside the domain, so for instance, images of the retina, it actually learns meaningful attention maps. It attends to the veins, which are very important when you come to diagnose this kind of images. And if you want to use this kind of model, they are readily available. So you can download them from Torch Hub. You can ask for a transformer. So this is a vision transformer, small size, so it's less layers, smaller dimension, and the patch size is 16. You can read an image. You can take the image and convert it into tokens because it's a transformer. And then you can run the tokens through the model and get the attention maps from the last block of the learned model. We can choose one of the heads, and then we can visualize the attention map of that head. So this is very easy to use. It's already trained. You don't need to train these models yourself. And let's try to investigate what are the representation, what are the features that this model learned, what they encode. So we saw this image when we learned about transformers. So we have an image. We took faces of animals, cats, dogs, and some lions. We extracted features, and we did PCA of the features for all these 50 images together. So this is from a supervised model. This is from a supervised ResNet. This is from a supervised transformer. And we look at the first component of the features of the PCA and the second, third, and fourth as an RGB image. And we see, we already saw that last time, that with transformers, we start with information that is position mainly, and we go to something that is more semantic. The resolution is kept the same because it's a transformer. With the convolutional neural network, we see that the resolution decreases as we go deeper because there are pooling layers. But again, we have something that starts with textures and go all the way to something that is more semantic. Now let's compare this PCA features to those trained by DINO. So we have DINO, the same transformer trained with DINO, the same ResNet trained with DINO. So it's the same architectures, but different, same data, but different training loss function. So we can see with DINO features, we see this degradation of resolution, but we see that the features correspond to parts in the image, although the resolution is very low. And if we look at the transformer where we don't lose resolution, we can actually see how it tunes to object parts. So it doesn't know semantics. It doesn't know this is a dog, but it knows that these are ears, eyes, and mouth. And if we compare this across images that we did the PCA for, we see it's the same colors for the ears, same color for the snout and the eyes. So basically, it knows to map these features to the same region in the feature space. So the same colors here in the PCA implies that the features are similar in the higher dimension feature space that they were trained for. So there were no labels here, but the fact that it needs to match local crops to global crops, it learns to associate and learn something about object parts. Okay?
Side of the pages for the DINO are the same as the transformers?
Yes. So we had some resolution trick here, but you can see this in the paper. We can play a bit with the, increase a bit the resolution of the transformer. But you get the same qualitative result even in the original resolution. We can also observe this in a slightly different manner. So we take images of animals. We have segmentation maps for them. So the segmentations were not used for training. It's only for this kind of visualization. So we can differentiate between the different features. And now we can extract features from all these images and associate the class label for each and every one of the features. So we have a global label for the animal if it's a horse, a dog, or a sheep, or whatever. So we have a class label. And we also have, from the segmentation, we have an object part label. And now we can take these features and project them to a lower dimensional manifold to visualize them. So we color each feature that we projected based on the segmentation map, and the shape that we're going to give the point that we projected is going to correspond to the semantic label of the image, of the animal. And this is the kind of projection we have for features from a supervised training. So we see it's very well clustered. And if you look at the clusters very closely, you see that there are many colors inside the cluster. It means that it grouped together many object parts, but it's the same shape. So the shape here, forgive me my old eyes. So these are squares. So it means that this is a dog cluster, and also dogs here. These are X's, so these are sheeps. These are circles, so these are mainly features from cats. So you see that they are grouped based on the class of the image, which makes sense because in supervised training, the features were trained to distinguish between different classes. These are the objectives that they had. Now, if you look at, on the contrast, if you look at DINO features, we don't see any clustering, these obvious clusters emerge, but we see kind of organization, this time based on the color of the descriptors, meaning that we have organization based on object parts, not on the semantic label of the animal. So it doesn't differentiate at this point between cats and dogs, but it can easily differentiate between legs, torso, and head, for instance. And this is very nice to see that this kind of property emerges, even though we didn't provide any labels or any semantic information during the training.
So how did you label the segmented?
So these are, this is from Pascal data set, so these are given. Again, we use this mask only for this visualization. We didn't use this mask for any training. It's just for this kind of visualization, and we really need to pick up the pace. So I'll skip this because we saw this kind of visualization when we talked about transformers. So what is the class token encodes? And we saw this kind of inversion. So the class token in DINO actually captures some appearance of the image in different layers. Again, it's flexible. So if we try multiple times to optimize for this, we get different kind of like soft representation. And this is about DINO. Any questions? Okay, let's quickly move on. Let's talk about mask autoencoder. Yeah, yes.
So we don't use them only for data that we don't have labels. Like it has another advantages.
Yes, yes.
So we use it also on labeled data.
You can use it for unlabeled data. You can train on ImageNet and then fine tune or only train a classifier. And you get hopefully a richer representation. Okay, so this was distillation. The main driving force here was the fact that we used different augmentations, and the augmentations actually contained a lot of prior knowledge that we have about the world, that you can actually associate objects with their parts. You can actually be invariant to some kind of color jittering and so on and so forth. So we're moving to a different strategy for self-supervised training. We are going to talk about mask autoencoders. So you saw autoencoder with Asaf. So autoencoder is trained to predict the image or the input that it has. And the fact that we have some bottleneck in the middle forces it to learn some meaningful representation so it can reconstruct the information from this information and with Asaf, we saw the variational autoencoder, so we had some constraint about this representation so that we can use the decoder in order to sample from a distribution and get different instances from the image set we had. So in generative models, we trained autoencoder, and we were mainly interested in the decoder part of the autoencoder. But in self-supervised, we are actually interested in the encoder part. So we are interested in this mechanism, in this representation that actually gives us this compact and hopefully meaningful representation for the images. And once we have this kind of representation, we can have additional supervised layers and do some supervised task like we did with DINO. So in self-supervised learning, we are more interested in the encoder part of the autoencoder. So this is autoencoder. Let's talk about masking approach. So masking was very popular in the natural language processing. So we learned about transformers in the context of natural language, and they were used extensively with self-supervised learning with masking. So the system, the paper that advocate that was called BERT, bidirectional encoder representation from transformers. And what it actually does, it takes an input, a sequence, a sentence, masks some part of it, and learn how to fill in the gaps. So for instance, I have my dog likes barking. I mask some of the sentence, and then I learn a representation that at the end will enable me to predict this masked token. So I don't need to provide any additional data or labels apart from the sentences, the input data I already have. And it's called bidirectional because they don't predict only the last token. It predicts even in the middle of the sentence, and you can predict from both directions. So you can learn how to fill the gaps. And it was a very effective method in natural language processing. So if something works very well in one domain, you try to mimic it. So you have an image, and you want to mask some of it. So mask autoencoder was definitely not the first one to do this. There was also BAIT, which is a BERT method, Siamese mask image modeling. But we'll focus on mask autoencoder because it gained a lot of attention. So what are we going to do in mask autoencoder? We're going to take the image, break it into tokens. This is a method that works with transformer backbones. And we're going to mask some of the tokens. So instead of a sequence, a very long sequence of token, we are going to have a very short sequence of token. And we're going to feed them into the encoder. Now we have a representation for each and every one of the tokens. And this is the encoder, this is the main part that interests us in an autoencoder in the context of self-supervised learning. But we need also a decoder. So we spread the tokens that we have, and we fill in the gaps with masked tokens. And now we need to predict all the masked tokens in the image. So now we have a decoder that takes all the tokens, both those that were encoded with the visual information and the masked one, and it needs to predict the masked tokens that we had. So there's no supervision. We don't need labels for this, only to match the learned tokens, the image patches, and we have loss over the patch value. Okay? And the loss is very simple. Just match those masked tokens. So how many tokens should we mask out? if we mask too few, the task would be very easy and we won't learn anything. If we mask too much, then the task is impossible and the model won't learn. So they tried several ratios of masking. So if this is the input image with all the patches, then this is what happens if we mask 15%. You can see some of the tokens are grayed out. This is 30%. And I think you can see that this is not a very difficult task. You can hardly notice that some patches were even masked here. And if you go to 50%, 70%, and even to 95%, then the tasks become very challenging. So just for comparison, in natural language processing, the BERT model used 15%. It only masked 50% of the masks because language is a very condensed manner of conveying information. So even if you mask more than 50%, you start to lose the meaning and you have no context to fill in the gaps. But in images, there's a lot of redundancy. We saw that when we discussed transformers in the first lecture on transformers, that you can actually make good prediction even with a significant portion of the image mask. And they showed that they can actually work with 75% and even slightly higher. And this is the kind of predictions they have. So these are the input images. They trained the mask autoencoder. This is with 75% masking. This is the masked input, what the model sees. This is the prediction of the model. So even if it sees only very small portions, it knows how to complete the object very well. Even if we increase the number of masked tokens, it still sees that there are several mushrooms here. Once we go to very high masking, then it loses a lot of the information. So it doesn't know anything about the pepper here in the middle because it has no evidence for this. But it's still able to complete something based on colors, symmetries, and so on and so forth. And once we have trained representation, it's very easy to fine-tune it for other tasks using smaller amount of labeled data.
Previous images that you showed, how many different images was in that set?
So this was trained on ImageNet, but I guess you can have. So ImageNet has two flavors. There's ImageNet 1K that has a million images, and there's ImageNet 21K, which has a few millions of images. So I think these are results with million images, but they also, I guess, they have bigger models trained on bigger sets of images. But you can see that it learns to complete very well. And again, once we trained the encoder, we can use this representation and then fine-tune on top of that some classification head or for whatever task we want. And actually, mask autoencoder is a backbone. It's used for a variety of tasks and other downstream models. And it achieves quite a remarkable performance. Let's take a break before we discuss some representations that mask autoencoder learns. Okay, so we talked about DINO, we talked about mask autoencoder, and we want to see if we can get some insight about the learned representation. So with DINO, we saw these PCA from shallow layers to deeper layers, and we see that as we go deeper, we get semantic parts that are mapped to the same region in the feature space, we have the impact of the positional encoding in early layer, like in all transformer architectures. And let's try to do the same thing for a trained master auto-encoder. So we are only looking at the encoder, and we're trying to see what the features it learns. So what we see here is that we see this nice maps in the early layers, but the colors don't match across images. It means that it mapped the features based on the appearance in the image, but it maps them to different regions for each and every one of the images. So it's based on the appearance rather than their semantics. So you can compare these nice colors here to the disarray here. At some intermediate layer, for some reason, I don't know why, the positional encoding kicks in. At deeper layer, there's a mixture between appearance and position, but at the end, we see some appearance and some semantic information appear, but there's still a lot of bias towards the position in the image. So in terms of semantic information, it's a gap. If we look at the embedding layer that takes these 16 by 16 tokens and project them into higher space, we can look at these projections, what they focus on. So this is the features, some of the features for the supervised model, and we see it learns this kind of center surround reaction, these boundaries, horizontal and vertical, and so on. And for DINO, we see relatively the same behavior. We have these oriented edges, we have these corners, some colors for the features, which is quite reassuring. But when we look at these, the same visualization for the mask auto-encoder, this is what we see. Can you guess what happened here? Yes?
Maybe if it's supposed to fill in the blank, it's going to learn how to go from the edge of the patch to the next one. So
Yes.
it really cares about what's on the edges.
So it pays much more attention to the boundaries of the tokens rather than the interior of them. So it's not a conclusive proof or anything, but it does indicate that there's not a lot of semantic information going on in the mask auto-encoder. Nevertheless, it has been used for a variety of tasks. It's a very popular model, and personally, it's a personal interest of me to see what's going on in there and can we improve on that method.
And you just improve it by doing the same thing you did in the previous class, but you don't give the image all the way to the edge.
So I talked with the people who trained mask auto-encoder, and I showed them this, and they say, well, if we mask 75% of the image, then most of the mask tokens don't touch each other. You need to complete very far away, so it doesn't make sense. But it's worth trying, and I think I will. I'm going to try, and maybe next year we'll have a better slide here. I don't know. Any questions on mask auto-encoder? Great. So our final direction is contrastive language image pretraining. So far, our pre-training focused on a single image and what information we can derive from it, either by augmentations or by masking. In contrastive learning, we are going to try and contrast different images or different signals. So if you are a pair, if you match, then you should have similar representations. If you don't match, then you need to have different representations. This is how you avoid collapsing into trivial solution and so on. And There's a lot of works on contrastive learning and contrastive self-supervised. We're going to focus on this CLIP model, contrastive language and image, because it's a very important model, and it's very important for you to know this work. So we talked about computer vision. We talked about natural language processing. They are both advancing very fast. We saw methods that deals self-supervised in computer vision. We saw BERT, which is a self-supervised in natural language processes. And why not combining these two modalities? So we're going to have a data set that has both images and text, but this time it's not just a single word label, but a free text that is associated with the image. For instance, my beagle Oliver likes food. This is the kind of text you have with this image, and we're going to train a model that will have two encoders. We're going to have image encoder, like transformer or ResNet. We're going to have a text encoder, another transformer, and we want these two embeddings to be the same. So we're going to project the text and the image into the same space. And if the text matches the image, we want these embeddings to be close to one another. And if the text doesn't match the image, we want them to be far apart. Okay, so we're going to feed, once it's trained, we're going to feed an image to the image encoder, a text to the text encoder, project them to the same space, and compute a similarity, which tells us how relevant the text to the image. So in order to do this, we need a data set. And this time it's a bit more tricky than just collecting images, because we need pairs of images and text. And you can say this is not exactly a self-supervised method. Okay. So in the original paper, what they did, they just crawl over social media, where you have tons of posts with images and the text that users wrote, and they collected hundreds of millions of these pairs. Another very important thing they did is they filtered this initial data set, because this is very random, very unbalanced. You can have a lot of images and a lot of text from specific concepts, and then you have very sporadic coverage of other. So what they did, they used Wikipedia in order to filter the text. So only concepts that appear in Wikipedia enough times are considered valid concepts. Otherwise, they are esoteric and they don't want to include them. And they insisted on having enough pairs from each of these concepts. So if a concept appears too much, they discard some of the examples. If a concept doesn't appear enough, they also discard it. So they have roughly the same number of pairs from all the concepts they curated. And they ended up with 400 million pairs of images and text. Unfortunately, we don't have access to the data they used. It's OpenAI. They kept everything private. But we have access to the model they released. And later on, people used the trained clip to curate an open set of text and images, and that was later used to train an open version of clip. So first of all, we have the data, a lot of pairs of image and text. And again, the text is not a single word, it's a very long sentences, and it has a lot of odd characters in there, emojis and things like that, and they feed everything into the model. And now we have the data set, and we can start training the clip model. So first of all, we tokenize the inputs. So we have text tokenizer and we have image tokenizer if you're using transformer. So for text, we have start of sentence, all the tokens, the words, and then end of sentence that actually gather the information about the sentence. In images, we have the class token that actually represent a global version of the image. We have image encoder and a text encoder. And they use GPT-2 for the text version. And once we have a representation, either the class or the end of sentence token, we can use a linear projection to project them to the same space. So we project them to a space with similar dimensions. And then once we have the joint embedding space, we have a loss over these representations. Yes.
Is the linear projection also learned? Or
Yes, it's all part of the, so everything is trained. I think, I'm not sure if they train the text encoder from scratch or they're using a pre-trained one. I'm not sure about this, but they train the projections, the projection layer, but it's a simple linear layer. It's a very simple one. Yeah.
Also, if they happen to use a pre-trained text encoder, would they make the learning rate for the text encoder be smaller so that it doesn't diverge much from the?
I guess so. I really don't remember all the details, but they have a very extensive paper and a very extensive blog post. And the important thing about the loss here is that it's contrastive. So we have pairs that match from the training set, and in the batch, we have a lot of examples that don't match. So in contrastive loss, we have an image, and for each image in the batch, we can have different augmentations. And for each example, we have the corresponding match, the positive example, and all the rest are negative. They don't match. They came from different images. And in a contrastive loss, what we are trying to do is we are trying to pull together the representation of the image with the positive example. So we want the representation for this pair to be as similar as possible. And we want to push away the representations for all other images. This is a contrastive. We want to contrast between positive and negative pairs. And this is done via this elaborated softmax. So we have the similarity, exponent of the similarity of the positive and all the negatives. So we want this term to be very high, and we want this term to be very low in order for the denominator to be very low. Okay? So we use the same contrastive loss for clip as well. So we have image embedding for all the images in the batch. We have text embedding for all the texts in the batch, just a second. And then we can compute the similarities between all images and all text in the batch. And on the diagonal, we have the positive pairs. So the first image needs to match the first text, the third needs to match the third, and so on and so forth. So in the loss that we want to increase the similarity on the diagonal and decrease along the off-diagonal entries. And this can be done using this term that we saw earlier. It's a contrastive loss that brings the similarity between text and images that are paired together and push away images and text that do not pair together. Yes, question?
The negative example they chosen randomly.
So it's a batch. You have 400 million pairs of text and images. The chances that a random text would match a random image in the batch is not very likely. So it might be that you have I don't know, very short descriptions that can match several images, but overall, if the text is long enough.
In the example you show, doesn't say in the text that it's a dog, so if I show a picture of a cat, it can match also. I'm wondering,
So the training data is large enough in order for this kind of signal to emerge. So yes, if the training set is not very big, then there's a lot of variation in images and text, and it's hard to match them. But if you have hundreds of millions of pairs, then signal emerge. So they trained, it's a very successful model, it's very useful, and what they show you can, what it's good for, what can you do with this kind of model? So we can do zero-shot learning, for instance. So, for instance, we have a new image, we want to classify it. So what we can do, we can actually have labels, now short text, an image of a plane, an image of a red panda, an image of a dog, and now we can encode these texts using the text encoder. We can encode the image using the image encoder and compute the similarities. And we expect the similarity of the image to best match the text that actually describes this image. And so this is done in test time. So it says you don't train anything here, you just classify the image based on the text, the very short text, it matches the best. So you can do a zero-shot classification with actually any vocabulary you want, as long as this vocabulary was covered in the training set of CLIP, which is very huge. And people actually showed that you can improve on that. So instead of just saying the name, you can actually write a short description. A red panda is a kind of an animal, a plane is a kind of transportation, and so on and so forth. And that giving this information in a text actually improves the classification of images in a zero-shot manner. They also showed that CLIP is very robust to appearance difference. So there are various variations on ImageNet that has images of the same classes, but under different domains, for instance, sketches or adversarial or all kinds of variations. For ImageNet R actually has different renderings of images. So you can have a banana, you can have a crochet of banana, a drawing or whatever. And models that are trained on the original ImageNet performs well on the original ImageNet, but if you try them on these out of distribution images, their performance degrades, but CLIP actually maintains very high performance even on these very different domains of images, because it actually saw hundreds of millions of images. And again, it's readily available. You can download CLIP, a pre-trained one from Hugging Face. You can get both the text and the image tokenizers. And you can do this zero-shot learning that we saw. So we have texts, and we can actually take the argmax over the similarity between the text and the images and get the probability for the image that we want. This is actually code that does this zero-shot classification that we saw before. It can also be used for a text-guided image generation. So if we have, for instance, a generator that generates images, natural images, so we have a loss over the discriminator. So we sample latent code, we have a generator, we have a discriminator, and we train the loss based on the distribution of the generated images with the set we have. Now, if we want to do condition generation, for instance, we want this generation to be a monkey with a banana, we can have additional loss using clip that actually matches the similarity in clip space between image and text. So now we can have loss between different domains. Instead of having losses only over images or only over texts, we can have a loss over these different domains. This is one way of introducing text guided generation. I hope you'll have another class on how it's done in a more sophisticated way, in a more integral way to the generation process. But this is just one way of doing this, using this very powerful clip representation. Well, it's not perfect. There's data that was curated over the internet, over social media. It has a lot of biases. So one paper that, in the original paper, they actually examined what kind of biases they have in the data. So they took another data set of 10,000 faces that should be, that is used for testing these kind of biases. So these are faces, they have labels based on ethnicity and gender and things like that. And now they can use this zero-shot classification of clip and classify these images. So they have these regular labels that they have in the data, and they add additional crime-related categories. For instance, suspicious, criminal, and so on. And some of the images in the dataset were wrongly classified into these suspicious criminal categories. And you can see that it's not even. So if you break down this error into suspicious behavior, you see that men are more likely to be misclassified into this suspicious behavior rather than women. So this is a kind of bias the model had. And if you further break down this error based on ethnicities, well, you see some ethnicities are less prone to be misclassified as crime-related, while others are more biased. There's more bias in the model towards them. And they also try to add some non-human categories, so you can classify the faces into a person, a woman, or so forth, but you can also classify them into a gorilla or some others. And then less than 5% were misclassified. So overall, it's not a bad thing. But if you break down this 4.9% into different ethnicities, then there is some problem here. And they did this experiment because I don't know if you've heard it, but Google Images very early on had photo search in their application. And one of the news that broke was that it misclassified people of color as non-human, which was very embarrassing for Google. So I guess this is why they added this kind of experiment into clip paper. So clip matches well between text and images, but it's not very accurate in terms of counting, for example. So if we give it this image of balloons and we ask, is it 2 balloons, 3 balloons, or 4 balloons? Although there are 3, it actually thinks that 2 is more likely here. So it doesn't really know how to count. And I think Michal and Tali had a follow-up work that they actually taught clip how to count. Again, relations is also very difficult. So is the ball over the cube or not? So it thinks that the cube is next to the balls. So relations is also something that is difficult to learn from this very loose pairing of text description and images. Another very interesting thing they showed in their blog is that they actually inspected neurons in the model, like Tali showed you in the visualization class. So they train clip, and now they optimize for an image that excites a specific neuron in the model. And they showed that they have neurons that are excited by specific concepts, and it can be excited by images. So for instance, a summer neuron is excited by things that are bright, but it's also excited by faces that are related to summer, and also by images that have text that is related to summer. And you can see this for West Africa, and you can see Ghana here and some other words related to this concept. They have a huge website with a lot of these visualizations. You can actually inspect different neurons, and they show that specific neurons respond to a concept, whether it's an image, a face, an emotion, or a text that relates. And the interesting thing about the text is that you can actually do adversarial attack using this. So you can have an image of an apple or an image of a poodle, and the model in a zero-shot manner classifies them quite well. But then if you add a text over the apple, it misclassifies it. And if you add some dollars over the dog, it now thinks it's a piggy bank, because it's very sensitive to captions on the image that were part of the data set that it was trained on. So to conclude, self-supervised learning is accelerating in the research field because it opens the gate for working with data that is uncurated, that is doesn't require manual labeling, and in other domains, getting the labels is very difficult. Self-supervised foundation models, for instance, CLIP, DINO, are very, very useful, and they are flexible, and they are used as building blocks for more complex systems. And I hope, so we won't cover this in this course, but you can see advanced segmentation models and tracking models that are based on these self-supervised features. And there are a lot of ways to do self-supervised, and we only cover these different directions of contrastive, distillation, and masking. But there are many variations on top of these. These are by far not the only 3 methods that exist. And you can read more about these different models. And there's also this self-supervised learning cookbook, where they have like an overview of many methods and approaches for self-supervised. Next week, Merav is going to start the topic of computer graphics and rendering. It will be the beginning of a few lectures on 3D modeling with deep neural network, which is a very exciting topic as well. And I hope you'll enjoy. Thank you.